Hi, so in this video we're going to go over how to calculate density and what's a quick summary of what Hooke's law is, because we're going into that material science now. So density, we know way back from our GCSEs, density is always equal to the mass divided by the volume. So if my mass is measured in kilograms and my volume is measured in meters cubed, that's how we know we get our units there of kilograms per meter cubed. So questions you might get is, how do we find the density of a regular object? So let's say I've got an object that is like a cube. So if I want to find its density, clearly all we need to do is measure the length of one side, because it's a cube, and we just do that length cubed to find what its volume is, and to find its mass, we make sure we use a balance. And we just make sure when we put it on a balance, we need to make sure the balance says 0 before we start. Okay, make sure we calibrate it. So calibrate it, just make sure that it says 0 before we start. For example, and we're going to go on scales to weigh myself if it doesn't really say 0 first, because I'm getting a wrong reading for my mass. So to find the mass, we just make sure that it says 0 first. We want to avoid that 0 error. Okay, but what if we have a liquid? So let's say I have a glass of milk, and I want to find out what the density of the milk is. What I need to do is I need to find what the mass of the milk is and the volume of my milk is. So what I'm going to do is I'm going to take my balance. So I take my balance again. I'm going to put a measuring cylinder on my balance. So I'm going to put my measuring cylinder on my balance. And clearly my balance now is going to have some reading. Maybe it's going to have a reading of 0.1, right? Because my measuring cylinder is going to have some mass, right? Because it's made of plastic. But what I'm going to do then is I'm going to recalibrate it. I'm going to hit the 0 button and reset that back to 0. So okay, it's 0. What I'm going to do now is I'm going to pour my milk into my measuring cylinder. So pour my milk into my measuring cylinder. And then we can see we're going to have a mass now on our scale. Maybe it says 0.4. So we know that the mass of our milk by itself is 0.4. So I've got the mass. And the volume I can just read off from the measuring cylinder. Key things about reading the volume that they ask for here is that you need to make sure you read from the bottom of the meniscus. So the meniscus is that little dip in a liquid. And you can see it if you ever have a bottle of water. If you look right at the top, you can see, or buy a bottle of Coke, at the top you can see there's a slight dip there. So you always want to read from the bottom of the meniscus. M-I-N-I-S-C, M-I-N-I-S-C-U-S, the bottom of the meniscus, okay? Also, you want to make sure that you read it at eye level, okay? So I make sure that I read the number at eye level. But you want to avoid parallax error, because if I was to read it from too high, what I'm going to get is a lower reading than what it is. If I was reading it from too low, I'm going to get a higher reading than what it actually is. So always make sure you read it at eye level, because you want to avoid parallax error. Okay, so that's our density. Okay, Hooke's law then. So Hooke's law is another one you would have done in GCSE, probably all the way back to lower school. Hooke's law, we know for Hooke's law that a force is directly proportional to the change in length, or sometimes you might say extension. And you need to make sure at A level you said that the force is directly proportional to the extension up until the limit of proportionality. Okay, and everyone always forgets to add that little sentence at the end in your A levels because you didn't need it in GCSEs. Make sure you add it. So what we're saying is if I got a graph of force against change in length or extension, because they're directly proportional, we always get a straight line through the graph. That means they're directly proportional up until that limit of proportionality. Because once we go beyond that limit of proportionality, it is no longer elastic. It no longer will return to its original length. When the forces are removed, it becomes plastic. And what happens then is you remove those forces, we can see that there's going to be a new change in length. It's called your limit of proportionality. So let's try some questions now. So if we look at the bottom question, it says, let's say we've got a hollow ball. So imagine like a ping pong ball, it's hollow in the inside. So I want to know what mass I need to make that ping pong ball, what mass of plastic. We know the density of plastic, and we know the outer radius and the inner radius. So you have to imagine, again, we've got this hollow ball. It's got some, let's say we cut it in half. We've got this outer radius and we've got an inner radius. So I know the outer radius there, it said is going to be 5 centimeters. I know that inner radius there is 4 centimeters. And I just want to figure out how much of this plastic do I need to make this ball, right? So just imagine that we've cut the ball right through the middle. There's my air on the outside, and this is the amount of plastic I need. So I need to figure out that little bit of plastic there, that's clearly just 1 centimeter in width the whole way around. So I need to know what mass of it do I need. So if I want to find the mass, I know to calculate mass, what we have to do here is the density times by the volume. So I need to figure out what is the volume of this plastic that I need. The easiest way to find the volume of the plastic is to find out what is the volume of a sphere that is solid 5 centimeters in its radius, and what is the volume of a sphere that is 4 centimeters in the radius. And then to find out the difference in those two volumes will tell me the volume of this plastic bit. So the volume of a 5 centimeter sphere is going to be 4/3 of pi times the radius, which is 5 centimeters, or 5 times 10 to the negative 2 cubed. Okay? And then the volume of my 4 centimeters is going to be 4/3 pi, 4 times 10 to the negative 2 cubed. Okay? Because volume of a sphere is 4/3 of pi r cubed. And we know that from your data sheet. So to find the mass, what we're going to do is for your density, which is 900 kilograms per meter cubed, we're going to multiply it by the change in the volume. So I'm going to do the bigger volume, which is 4/3 of pi times by 5 times 10 to the negative 2 all cubed. And we have to subtract away 4/3 of pi times by 4 times 10 to the negative 2 all cubed. And that will tell us then just the volume of that plastic material that we need. So on our calculators, what we're doing now is we're going to go 5 times 10 to the negative 2 cubed. We're going to multiply by pi. We'll multiply by 4. We'll divide by 3 to find out what the volume is of that outer radius. And now we're just going to subtract the volume of that inner radius, which is going to be 4/3 times by pi times by 4 times 10 to the negative 2 cubed. So I can find out what the change in the volume is, and then I'm just going to multiply that change in volume by 900, the density, to find what the mass is. I get a mass there of 0.23 kilograms. That's the mass of that plastic material I need. However, that's a lot of math to have your calculator in one go, so I would just double check it all the time. So again, what you're doing is you can also take out your 4/3 out of the bracket and just do your 5 times 10 to the negative 2 cubed, take away your 4 times 10 to the negative 2 cubed. So you want to do that, you just do 5 times 10 to the negative 2 cubed, take away 4 times 10 to the negative 2 cubed, multiply by pi, multiply by 4, divide by 3, and multiply by 900. And I got the same answer. So again, just to show you what I did here when I simplified, what I said was instead of writing out like this, you could technically factorize out your 4/3 pi. So I could write 900 times by 4/3 times by pi multiplied by 5 times 10 to the negative 2 cubed, take away 4 times 10 to the negative 2 cubed. Okay, that's what I did the second time, just to prove that I got the same number in my maths. Okay, next one then is we're doing like a Hooke's law example now. So let's imagine we've got a sign. It's non-uniform, because remember uniform means we can say the mass to be evenly distributed, or we can say the weight acts in the center. This clearly is non-uniform because the weight of the sign is not acting in the center. It's acting 0.65 meters along from point A, or 0.15 meters along from point B. It says that spring A and spring B both obey Hooke's law, so we know that the force is directly proportional to the change in length. It says we know the spring constant is 240 newtons per meter. I want to find the change in length of spring B. So in order to find what the change in length of spring B is, I know F equals spring's constant times the change in length. So if I know the spring's constant, which is 240, I want to find out what the change in length is. Clearly, I need to know what the force is on that spring B. So I want to find out what that force is on that spring B. So if I look here and I think, how can I calculate the force on that spring B? Clearly what we want to do here is we can see there's been a moments problem. And in moments, remember, we always take moments about the point that you want to ignore. So I've made a later video, or an earlier videos are there on moments. So have a look back at that one if you want to revise how to do moments. So again, we take moments about the force we want to ignore. I'm going to ignore any forces at A. So when I take moments about this point, I'm going to do its force times its distance. So I got here is 18 multiplied by 0.65 is the moment trying to pull it in the clockwise direction. That's going to equal the moment trying to pull it in the anti-clockwise direction, which is that force at B times its distance away it is. And the total distance here is my 0.65 plus my 0.15, which is going to be my 0.8. So now I can calculate what that force is at B. So I'm going to do 18 multiplied by 0.65, and then we're going to divide that number by 0.8 to figure out what that force is. And get a force there of 14.625 newtons. So I found what my force is. So now I know the force, which is 14.625 newtons. That equals my spring constant, which is 240, times by the change in the length. So if I find that change in length now, I just take my number and divide it by 240 to find what that change in length is, and I get 0.06 meters. So my change in length is 0.06 meters. So, grand.